Okay. All right. Okay. So I will do it later today. Okay, to record the first lecture. So yeah, it's too bad. Sorry. That's really very fun problem. Okay. So I think I will record the main. Maybe it may not last 45 minutes or maybe even longer. I don't know. Okay, I will see. Okay, maybe in the evening I do it. Okay. Yeah, in the afternoon, I don't think I have time. Have to prepare for to finish the final exam paper. Oh yeah, by the way, for the final exam, okay. Yeah, since I mentioned it, okay, for final exam, I think you want to listen to this, right? We are mainly concentrated on counting, relation, and graph theory. All right. So counting, binary relation, and the graph theory. Of course, the main part will be graph theory because we spend 3 weeks. All right. For counting problem, basically, pigeonhole principle will be still there, and permutation and combination with repetition. So that's it for counting part. Of course, some basic things, a product rule, additional summation rule, addition rules, these kinds of things. Of course, will be there. The basic things. Okay. We may need something from first half of the term. Maybe we need something, the constellation or big O notation. Of course, these basic things are logic. But mainly we'll concentrate on these 3 parts, counting, binary relation, and graph theory. And the difficulty will be similar to midterm example. Midterm exams. Okay, will be similar. All right. Okay, so let's continue about walking around in a graph. So we have paths, then we have distance. Once we have path, then we have distance. The length of a path, of course, is number of edges involved in the path. So given 2 vertices, then we can talk about their distance. So typically we use DUV to denote the distance. That means number of edges there can be many paths. For example, here we have 2 paths, this one and this one. So one that has minimum number of edges is called the shortest path. So that's shortest path. All right. Number of edges is called distance. Minimum number of edges in any path between U and V is called the distance. A number of edges in a shortest path is called the distance. So that's called the distance. This one is called distance. All right. So that's called distance. And sometimes people may use other notation for distance. You can see, you may find use delta or use distance. D distance UV. You also may see these 2 instead of this one. Okay. Now for directed graph, for digraph, is not symmetric. Distance from U to V and from V to U may be different. So then we use UV distance and VU distance. For some graphs, they may not be equal. For example, the graph may look like this. Here's a digraph. Now distance from U to V equals 3, and distance from V to U equal 2. They can be different for digraph. For a simple graph, for graph, undirected graph, distance will be same. So DUV equals DVU for undirected graph. Because that's the metric. All right. Okay. So that's the notion of path and the distance. Of course, when we talk about distance, very often edges will have a number associated with it. For example, if we use distance to model distance, physical distance, and the edge corresponding to street. Okay, so look at the following situation. All right, so when we talk about the distance, so we can use intersection as vertex and the road between them as an edge to model it. Now you will see that if we do this, if we talk about distance for this kind of situation, then we'll associate each edge with number to indicate the actual distance. So then it will be associated with number, so maybe a real number. Here maybe say 120 meters, maybe. So here maybe 80 meters. Here is 150 maybe, right? So then the graph we obtain is called a weighted graph. Where this one is a function, is a weighting function that gives edges a weight, maybe real numbers or positive real numbers. Depends, okay, depends situation of integers or real numbers. Sometimes allow zero, sometimes it does not allow zero. So really depends on situation. All right. But the point is each edge will get a number associated with it. So that's called the weighted graph. Sometimes the weight can be even on vertices. So each vertex maybe also has a weight. So in general, this one can be a function from both edge set and vertex set, maybe two real numbers in general. So that's very general way of giving a weighted graph. All right. The point is each vertex or each edge can have a number associated with it. So we get a weighted graph. Now for weighted graph, the distance, of course, naturally will be sum of weights on edges. So of course, so we have a path. So here we have a UE path. All right. Now for this path, we have its weight. This of course sum of weight on edges. So this one is denotes edge set. All right. So of course, the weight of a path is defined as sum of weights on edges of P. All right. So we have its weight. And this weight is called length of P. So have length of P. Okay. So for each path, we have its length, that's sum of edge weights. Now distance, instead of number of edges, I'll call this one because the length. So instead of number of edges, it becomes length of shortest. Shortest, of course, means path with minimum length. Shortest means path with minimum length. Okay, so that's very intuitive. So from paths, we have notion of distance, and then we have notion of shortest path. And now we can say that all computational problem actually is a problem find the shortest path in a graph. As we discussed initially, any computation can be modeled as a graph. We have different configurations, okay? So there are edges between different configurations. So what we want is from initial configuration, typically that's defined by input, go to our required configuration. So in order to go from initial configuration to the final configuration, we want to go as quickly as possible. So finish computation in shortest amount of time using this amount of time. So that's saying we're looking for shortest path, all right? So that's very called for the problem of finding a shortest path. So that's after to solve the following fundamental problem, how we can find the shortest path in a weighted graph. All right. So this problem is easy in the sense it can be solved in polynomial time. In that sense, it's easy. So it's much easier than many graph problems, which are so-called NP-hard problems. So in this case, it's very easy. We have a classical problem called the Dixer algorithm to solve it roughly in say in m and n plus n log n time. So we have a classical algorithm to solve this problem in polynomial time. It's very close to linear time. Okay. So in this sense, the problem is easy. Of course, it's beyond our scope. We'll not discuss algorithm for this course because this one mainly is mathematics. Okay. But in algorithm course, we'll discuss this one in details. All right. So this problem can be solved, but the problem is the search space typically is huge because number of configurations. For many problems, it's very huge. So in that sense, it's also difficult because of the search space is huge. So we cannot expect to use this algorithm to solve all computational problems in practice. So you may try it, use so-called exhaustive search. We can always find a path from initial configuration to final configuration. If it is possible, we can always find it using, say, exhaustive search. But time it takes will be huge because the search space, number of configuration may be huge. So in that sense, even this problem is not easy. All right. However, whenever the graph is of relatively reasonable size, so when n is not very large, then it can be solved relatively quickly. All right. So in that sense, shortest path problem is not that difficult. On the other hand, so here is shortest path. Naturally, one can consider longest path. So instead of shortest, one can consider longest. So in this case, even the graph is unweighted, the problem is very difficult. So we can forget about unweighted graph, because even for unweighted graph, it's very difficult already. So let's see what we mean by longest path. We want to find a path with as many edges as possible. So basically, this one we want paths So instead of shortest, we look for longest. Then the problem becomes very, very difficult. So let's see, maybe I can, at least will give you two results related to this one. Okay. So this was very, very difficult problem. For example, let's see. Of course, the example is easy. For example, find the shortest path between you and B is very simple. It's easy to see. For this simple graph, small graph, it's easy to see. You see it immediately. Three edges, that will be shortest, right? Only three edges. It's very easy to see it. All right. Now, what's the longest one? So this one, four edges. But there another one that's actually five edges. We can go like this. But is this best possible? So in this case, I think it is. But yeah, it is a simple path. I think it is. In general, it's not easy at all. All right. Now, what we can guarantee is, let's see. Okay, so just two notation. Typically, we use delta of G to denote maximum vertex degree, and small delta of G to denote minimum vertex degree. So for this graph, I think the maximum one is 5. So this one have largest degree. Minimum is 2. This vertex has degree 2. All right. So here I will give you a small theorem. What is continuous with delta of G edges, where delta is minimum degree. So actually, you will see actually it does not seem to play important role for minimum degree. So this graph, minimum degree is 1, but the path length can be as long as possible. Actual path length is n minus 1. So here is only guarantee a path of length delta. So if minimum degree is 1, it's only guarantee their path of length 1. If minimum degree is 2, it's only guarantee a path of length 2, only 2 edges. Okay, it does not seem to be much, but that seems the best we can do because that's an example. Minimum degree 2, I only have a path of length 2. Now, how can we prove this one? As I mentioned a few times, it's always not easy to prove something in graph theory. It's really not easy. So therefore, I will give you an idea of how to do this. Okay. So of course, intuitively, we have to understand what's going on. So what's going on is I can start with a vertex. All right. Now just draw a path from this vertex and maybe use and draw a path. All right. So because minimum degree is at least a delta, so this one, if degree is smaller than delta, I can keep on growing. Keep on growing. Of course, for this vertex, it may adjacent to some vertex inside and maybe adjacent to vertex outside. So if we look at this vertex, So under what condition can we always grow us to outside? So in the worst case, maybe for each vertex, it's always adjacent to vertex inside. Because minimum degree delta, it can be adjacent to inside at most delta vertices, right? Minimum degree is delta. So whenever this part is smaller than delta, I can always grow a vertex, grow the piece, to add one more vertex, adding one more vertex. So that gives us an idea of how to prove it. So it seems I can keep on growing parts, but it's not easy to say it clearly what's going on. So I draw it, I think I can convey the idea by doing things like this. So if this one is has one more button outside, I can keep on growing. I keep on growing. But how can I make it formal? All right. So what we will do here is, as often in graph theory, that's what we will do. So So what we do is very often we consider extreme case. So here extreme case is that suppose we have a longest path between two vertices, UV. So that path is as long as possible. Among all possible paths, we have a longest path between two vertices, U and V. All right. Okay. So we assume we have such a path. If we always have such a path. Now, if length of P typically length we use L of P instead of W of P. So L of P number of edges in P. Okay. So if it contains delta edges already, then of course we're done. All right. Otherwise, number of edges here inside will be less than delta. So otherwise, the number of edges here, all right. Now, what's the number of vertices here? Number of vertices. Then consider this part. All right. Otherwise, okay, so this notation is P without this end. All right. So P without this end. So this part, number of vertices is less than delta. Right? Okay. Now, by definition of delta, we know delta degree of V at least delta G. Because the definition of minimum degree, we know degree is at least this. Now this vertex must be adjacent to at least one vertex not inside here. Not belong to this point. All right. So this one, even if adjacent to everyone here, it's not good enough, right? It's not that good. Out there smaller than delta. So this one must be adjacent to a vertex. Now what we get? We get a longer path. All right. So that implies P plus this new path dx. Okay, maybe just use edge notation, so it can say just plus. Notation, Wednesday we discuss these notations. Dx, say, this one is longer than P. So we get a path longer than P. So that's a contradiction. Contradiction to assumption P is longest path. So here we get the contradiction. All right. So because this contradiction means number of edges here must be at least delta. So only this one will happen. So this part will not happen. Okay. All right. So very often when we prove something by considering the extreme situation, because extreme situation will give us more structure. So here long is a certain structure. So because this structure, we can argue something will not happen, because if it happens, it's contradictory to this assumption. So here we get a longer, which is impossible. So eventually the only thing can happen is actually this one. Number of edges must be at least a delta. So that shows that graph always has of length at least minimum degree. So that's not too much, but it seems that's best we can do, because longest path problem is very, very difficult. Right? So that's one of them. Okay, so here I want to emphasize undirected graph, because we are discussing undirected graph, because things may be different from directed graph or digraph. Okay. So here we'll emphasize, I put an undirected graph to make sure that we're talking about undirected graph. So what it means is if I take any two longest paths, then they must have one vertex in common. So here two longest paths means longest path and the second longest path. So the graph may have only one longest path. For example, this graph, it only has one longest path. So what do we mean? Two longest paths. So that means one longest is the longest path and the second longest path. If we order paths with respect to their length, So then we have longest path, second longest path, third longest path, and so on. The first two maybe have same length, okay? So that's what we mean by two longest paths. So if you take two longest paths, then they must share common vertex. So for example, this one. Excuse me. Okay. So this path and this path share a common vertex. Actually, these are not two longest paths. The longest path actually is this one. This one is the longest path of length 6. Another one where we have length 5. There are actually a few of them. So another one is this one. So these two paths share these 4 points, 4 vertices. So even for weighted graph, so this one even weighted, this one even weighted. But be careful here, weighted, okay? You will see what I mean for weighted case. So let's prove it for weighted case, all right? Right, now we have a longest path and second longest path. We want to show that if this P, so this P, this Q, so somehow they have to cross. So they must share a vertex. So that's the meaning of the theorem. So that's common vertex. So this one is a common vertex. So you must have this situation. They can share more than one vertex. All right, so that's what we want to prove. So how can we do it? So assume very often we use contradiction, prove by contradiction. Assume their vertex disjoint. So assume they do not share. All right, so we have two paths, their vertex disjoint. I forgot one thing. Sorry, so here should be connected. Sorry, here should be connected as well. Connected, it's very. Graph is connected. Otherwise, they, of course, they cannot share. They may not share. For example, if this one is not connected, if that's a graph, of course, that's the longest one. Second longest one is share the points. They share the vertices. Or sometimes we also call the vertex as a point. Another name for vertex is point. But it's in very old time we use point node, as I mentioned. Sometimes called point lines for edges. Only an old time when you use points and the lines. Nowadays, typically use vertex, sometimes nodes. The graph has to be connected. How do we have this situation? Then what happens? Now, it's important that the graph is connected. So connected means for any two vertices, they are always a path. So that means between these two paths, there are at least one edge connecting them. Otherwise, the graph may not be connected. Okay, or paths. So between somewhere, some vertex here and some vertex here, there must be a connecting them. Yeah, so let's PQR, maybe call this one. If otherwise the graph cannot be connected. Since it's connected, there are paths between say this vertex and this vertex. There are always a path between these two vertices. So somehow it has to pass from this path to this path. So there will be paths between some vertex here and some vertex here. All right. So we have the following situation. Okay. Now P is the longest one. Q is the second longest. So for these two parts, We without loss of generality, maybe we can just assume the drawing is maybe I make this one a little bit shorter. So we can assume this part is no shorter than this one. So this one is longer part. So similar for this part, this one is no shorter than this one. So let's see, let's divide them into, so maybe this top of the P top. So if in this drawing, so it's bottom, so here Q top and Q bottom. Okay. So assume that LP, the top part is no less than the bottom one. Similar to Q. Okay. All right, suppose we have this situation. Now consider this path. So that's a new path. We consider this new path. What can we say about this new piece? Compare with Q. If we compare with Q, if we compare their lengths, so we have length of P time, we compare length with Q. What can we say about this? This one is always more than this one. If we for weighted graph, if edge weight, in weighted case, if weight here is positive integers. If it's a positive, if each edge weight is positive, when it's a positive, we always have this situation. If we allow negative weight, that may not happen. So it's not told. If we allow negative weight, okay. But if all edge weight is positive, we always have this new path is longer than Q. Because this part is longer than this one, this part is longer than this one. Of course, this part is longer than this one. And so this no shorter than this one, no shorter than this one. This one plus this one is no shorter than Q. Then plus this one, this positive. So it will be longer than LQ. So that contradicts to Q is second longest. This one contradiction. Right. So therefore, we cannot have this case. So this one cannot happen. So any longest path and the second longest path must share vertex. So here two longest path means longest, second, longest. So these two may have same length or may have different lengths. So because of this, if this one longest, this second longest, then they must share a vertex. All right. Okay. So that's second example. And third example is a kind of algorithmic, has something to do with actually find the path. Okay, so let's see. I will finish it with this example. All right, now I consider a special kind of graph called the tree, which I will discuss it. Um, if not Wednesday, then next week. Okay, I haven't decided whether we discuss it on Wednesday. A tree is a graph that is connected and has no cycle. So it's a connected graph without cycle. The reason we call the tree because you can draw like tree. That's where its name comes from. It looks like a tree. So there's no cycle. It does not have this kind of cycle. So this is called a cycle. We don't have cycle and it's connected. So this is called tree. If without this condition, if just drop without cycle, naturally, then we call it forest. It does not need to be connected, then it's called a forest. It's because a collection of trees. So we have another one maybe. So it has a few components. Each component is a tree. So that's called a forest. Okay. A tree is a connected graph without cycle, and a graph without cycle is called a forest. Okay. The problem is to find the longest path in a tree. In general, finding the longest path is extremely difficult. Extremely difficult. Very difficult to find the longest path. Even graph is unweighted. But for tree, even if it's weighted, there are a very simple way to find the longest path. At least two different ways. So here I will give you one way. Okay. So let's just work on one example. So that's where the tree. Okay, you see it's connected and without cycle. Now let's make it a weighted tree. Each edge has a weight. All right. Now I want to find the longest piece in this tree. Okay, if the graph very small, of course, it's easy to see it. But when it's large, it's not easy at all. We have to use a systematic way to find it. All right. So in this case, what we'll do is start with any vertex. Actually, start with the vertex. So maybe this vertex, U. All right. The starting from U, we find the longest path from U. All right. So we find the longest path from U. How can we find it? It's not trivial, but it can be done. It's not difficult at all. Find the longest path. So we can just here. So the first one must use this one, of course. The next one we can take this one or this one. Even we consider all possibilities, it will enable us to find it. All right. So for this case, maybe let's see. I think it's this one. It takes linear time. The time it takes will be linear time. If we just consider every branches, all right. So if you heard of this thing called the DFS or DFS, search tree, DFS, so either way will enable us to find it. It's very simple, okay? So we can find the longest path from U to another vertex. All right. So it ends with a vertex, say V. However, this path may not be a maximum longest path. So in this case, let's see, I don't know whether it is. It's 17. The length is 17, right? 10, 17. It is not the longest path. Yeah, it is not. Cell 122. Okay, so this is not the longest path. So how can we find the longest path? What we do then, so that's first step. Second step, then starting from this end, we find the longest path. So in this case, this one will give us longest. Okay. So after this one, we'll find us this longest path, I think. I between the three. I think this one is longest. When I start with this one will find us this one is longest path. Okay. What can happen is do it twice. One from create from one vertex, and from the end of longest path and from the first step. Then the longest path, and this one guarantees as the longest path. And how why it works, I think I will leave it as homework. Ask you to prove that this one really gives us the longest path in a tree. All right. Okay, I think I should stop here because I overrun by 2 minutes. All right. So we'll see you on Wednesday. Okay. So I will redo the first lecture later today. Okay, to record that mountain range sensitivity, synchronize the climate problem. Okay. Okay. So see you. Thank you. Oh yeah, sheet. I think it's sheet paper. We haven't decided. I think it's 2 pages because we're still discussing it. Uh, once finalized, I will announce it. Okay. I think basically maybe 2 pages double size or 1 page. We haven't decided yet because it's not only my section. There are 4 sections. All right. Okay. Cheat sheet. Yeah. I think we will. Okay. Yeah, I will release the scope in the course homepage. Okay.